let me just give some idea of where we're going. Someone asked me about using Lagrangian techniques and Hamiltonian techniques and so on. And I think in a way we're not, that's a very formal way of doing things, a very formal way, and it's very beautiful and very nice. But we are not so far away from it with the way we're doing it. Without doing all the formalities, we can say what we have is a function which we will call h, which is a function of p, and in general one uses q for the coordinate. But let me stick to what we've been using. We've been using x. So we've said there's a momentum and there's a position, a coordinate. And this function h is a function p, is a function of p and x. So you give me a p and you give me an x, and I put it in there, and then I calculate an energy. So I say my energy is gotten from a function which depends on p and x. And this energy, of course, I mean this function, so this is for a specific p and x, and so this function, the cases which we have considered now, is this. This is the Hamiltonian function. It is p squared over 2m plus a potential v of x. Okay, and what people will do, for instance, they can, if normally in physics, they will not start with Newton's equations. They will start with either with the Hamiltonian or with the Lagrangian, and then they can do everything from there. And I have been starting from Newton's laws and showed you how we calculate energy in various ways. And we've come to this and we've concentrated on energy. And the energy is basically the quantity you get out of the Hamiltonian, the Hamilton function, the Hamilton function. So, but now this, if I just write down this, you may say, well, but that's not, you want to know what is the acceleration and all these things. You don't just want to know the energy function. And there, the Hamiltonian theory tells you that p dot, the derivative of p, is equal to minus dh dx. And so if we use it in this, this is general. And if we apply it to this specific case, we then get this minus dv dx. So I can, and p dot is x double dot over m. I mean, it's acceleration basically. Huh? So that you can get from the Hamiltonian immediately like this. Huh? And similarly, you have two equations, Hamilton theory, where you then say x dot is equal to dh dp. And so this is the way it works. You have an h which depends on p and x, and you can get x dot, and this you get this way. And if we apply this to that equation. So what do we get? P over m. P over m, which is v, yeah? In our language, a small v in our language. Yeah? So you see, by just writing down this and knowing the Hamiltonian equations, you know everything which you knew from Newton's laws in any case. Now, what I'm going to do from now on is I'm going to go to more dimensions. So we've done this in one dimension. The one-dimensional problem is just this thing falling down, or the swing. It's just in one dimension. But in general, if things move, they move in 3 dimensions. And so my h now in future will depend on p as a vector, which means that this is h is a function of px, py, pz, and of x, y, and z. So it depends on six things. Huh? But what is still true, the Hamiltonian equations are still true. If I want to calculate, for instance, px dot, then the thing that I will have to do is to calculate minus dh dx. And similarly for y and for z. So these are associated. The x and the px, the position and the momentum, and this is associated to that and this to that. And so, and in this way I can also then do x dot by the same way, by doing dh dp x. Now what is nice about this formalism is that I can immediately expand it to more particles. I can say, well, what do I do if I have 2 balls and they attract each other? Say the Earth and the Moon, or something like that. Then the Hamiltonian theory tells me you just carry on doing this. You just say, well, there's a h now becomes a function of the momentum of the first particle and the momentum of the second particle and the position of the first particle and the position of the second particle. So it is a function of now not of 6 things, but of 12 things. Huh? And this I can keep going on. I can do it for 3, and I can do it for 4, and I can do it for very many. I can write this will become a function of many momenta and many positions, and that is the way one would do many problems in physics. But let me just, and then I'll go back to what I do. This is just a sort of an interlude showing you where we go. If I do this thing with 2 particles, then the structure of that H will be what? it will be another h. Let me put it the h of particle 1, which depends on p1 and x and r1. So this will be basically the momentum and the potential which particle 1 has. And then it will be the same thing for particle 2. And this would mean vector. Thank you. This would mean that I consider two particles separately, that they just one moves and the other moves, and I don't really need to talk about two particles. I can study the one and then I study about the other. But basically, if I have two particles, they will interact with each other. The Earth attracts the Moon, and the Moon attracts. There's an interaction between these two particles, and so there will be another term here, which can depend on, say, in general on all these coordinates, but we can say it will depend on R1 and on R2. You see, and what we are doing, and this I can again expand. I can have many particles here, and they all interact with each other. And so then I will have R1 interacting with all the other particles, and so on. And so it is just a complicated business. Now what we do in this falling body case, we're just looking at one part of the Hamiltonian. We're just looking at the ball which we are watching. And we're not looking at all the other balls, the little atoms and so on that crash against it. They are H2, H3, H4, H5, and there are many of them. No? And the statement of energy conservation actually says that this Hamiltonian, with all its particles, is conserved. So that is conserved, and when we look at a part of it, then of course it needn't be conserved, because the total energy is conserved, but not necessarily the movement of the Hamiltonian for this one part, because it interacts with all the others. And so the energy conservation is in that sense retained if you say E I get by calculating the full Hamiltonian of all the particles. Okay? Any questions about this? You understand it? Makes sense? Okay. Now, what I want to do today is, I don't want to do this program. It's quite difficult. But what I want to do is, I want to go to this thing, to 3 dimensions. I want to do problems in 3 dimensions. So we can also calculate, use Newton's laws, as we have seen. If I do that in 3 dimensions, I have said how we can get P. So we will get P as a vector. Would be what? P dot as a vector, sorry. P dot as a vector. So I'm looking at this. So what will P dot be as a vector? So we know what Px is. It's basically the yeah, and we have a little way of writing it. How do we write that? Dx. We say it is the gradient of h, huh? and this is P and R, and we say this is the in this case, if P looks like, well, I haven't written it down, but if P looks like this, then it is the gradient is the light not good? The gradient of V of R. Huh? So more in more general, or not necessarily more general, but let me start off and say we have a force which is a vector in 3 dimensions, and the force can be written as the gradient of a potential. Is this always possible? Can you write any vector function which depends on a vector as the gradient of some other function? So what's the condition? Well, I don't have energy yet, but you are on the right track. You must just use your words a little different. You have what we call a conservative system, and a conservative system on a force is conservative is if what? Yeah. So if you can check any force whether it is conservative by just doing checking its rotation, and then if that is 0, then you can write that, and the forces we will be looking at are conservative, and they will fit in. Only then is it possible to put it in this way into the Hamiltonian problem. No? So if we have what is a typical force, or for that matter potential, which we are looking at, which say between two big a planet and the sun and things like that? What is the force? The gravitational force, that looks like what? Okay, so the force is equal to minus G M over, I'm considering now a big thing and a small thing, and and if they're equally big, you have to go to reduced. You have to take care of the movement of the center of mass as well. But if you take one big thing and one small thing, then you can just look at the motion of the small thing, and that its distance, that's a big thing, and this is the small thing, and the distance here is r, and the force goes like that. And so what is the potential? One over r. And we will call this whole thing, we will call K with a negative, just in order to save a bit of writing. Am I finished? Oh no, was this right? This is a vector. So it's a unit vector in the r direction. Why is it minus? Because there's attraction. If I measure r, it depends from where I measure r. But if I measure r from here, then it must be minus, because it pulls it back. It pulls it to smaller r. Okay. So then, in this case, my unit vector is showing that direction. Okay. And so if I do the gradient of this, I do in fact get that. Okay. So now we must calculate say we use Newton's laws. We use this. Then we want to calculate the equations of motion. We would like to use. It's what? Positive. If I differentiate this, I get minus 1 over r squared. And there's a minus there.
It's attractive potential.
Yes. So?
Should be positive.
The potential should be positive.
Otherwise, the force should be positive. No, one of them should be positive.
No, but
the other is negative.
no, but you're missing if I differentiate this, I get minus 1 over r squared. So there's an extra minus sign. So I have a minus and still another minus.
Yeah. It should be positive.
What should be positive?
The potential. If you say that what we are comparing to define potential, we are actually setting the initial potential between
The usual potential.
the actual potential is a different potential. And then we have the difference.
No, so speak slowly and clear.
Potential there is a difference in potential. But we have to set the potential the initial potential as determined so that we get a
No, but if a thing is at infinity and it is zero, and I bring it into it is being attracted by the sun, it gets kinetic energy. And so it more and more and more as closer as it comes. And that kinetic energy has to be cancelled with the potential energy, which needs to be negative. Understand? I think this is right. If I'm wrong, then you can... Abraham, are you happy? Is it right? It's right? You right? With your infinity? From infinity you come? It's a good point. Come from infinity where you set the potential equal to zero if the things are far apart. And now you bring it in. And in order to bring it in, it will gain kinetic energy. And to keep your energy at zero, which it was initially, you have to have a negative. You have to have a negative potential energy because the two together must remain zero. Huh? Okay. So it's a nice physical argument. Okay. So I'll draw the potential here. This is now R, and this is the potential, V of R. This is zero. This is when that guy sits right in the middle there, which is not quite true because this is an extended object and so on. So we can't go zero on zero, but that's a different point. But if I plot this thing, it looks like this. Okay. So what you were saying is I get a particle here, and it moves in, and when it's here, this is its kinetic energy, as we have made. So this distance from where it is there, the potential energy it had, which is a half mv squared. Ibrahim?
You mentioned before that we measured R from the negative side, that would make the force negative. But now we will go R positive. That's why I was talking about if the potential goes like minus, so the force must be positive, and other vice versa.
It just looked as though I measured it from the negative side. My argument, maybe I drew this wrong. I did. So I'll just change it around. I'll draw the big guy here, and the small guy here. And now this is the positive R direction. But the force is in that direction. Okay? Because they attract each other. Okay? And now this point is this point here, and I am bringing that guy in, and it's being attracted, and it needs a force in the negative direction. Okay? That's my positive direction. Happy? Okay. Now if we want to solve this in general, solve such problems, we can say we need to mr is well, it's the force, huh? And the force here is k over r squared. I'm taking the minus into the k, I make it the capital K, and then in this direction. So this is a vector sum. So this I can solve in many ways. I can write r in terms of x plus y plus z. So this for me is a unit vector in the x direction times the x component of r, and this is a unit a vector in the y direction, and so on. And so I can just easily write these equations, but here I have an equation for x, and I have an equation for y, and I have an equation for z. But unfortunately, this thing pulls them together, because here I don't have x and y and z separately. As I have over there x squared plus y squared plus z squared, the square root of it. Huh? And so it's oh, sorry, the potential is the square root, yeah. Sorry, just like that, yeah. Thank you. Good to have good guardians, guys who watch you. Thank you very much. And so, nevertheless, as it is here, I can't just do the problem in the x direction, and I can't do in the y direction and in the z direction separately. I have to do them together. And so that's a real three-dimensional problem. But what I can try to do is I can go to other coordinates. I change my base of coordinates, and I say, well, I will go to the coordinates of anything. Will have the coordinates r, theta, and phi, whereby I have this sort of picture. This is my z-axis, this is my y-axis, and this is my x-axis. And from the z-axis, I switch over like this and make this angle theta. And then I will take this point here and I will put it down here, and I will draw this line, and then I will call that phi. So what I'm doing is I'm taking a thing like this. Say this is y, and this is z, and this is y here, and this is the x direction. So I'm taking this thing and I'm projecting it onto the different planes, and so I'm doing it in this way. And if you do that now, then you can, and let me write it down, because last night for the first time I had it wrong when I tried it. So I can now write the unit vector. So I want to write my vector now, my vector r. I want to, or any vector, I want to write in terms of these new coordinates, the coordinates theta, phi, and r. And then the way I can do that is Do you know this? Sine theta. And that is sine theta sine phi. And then there is plus z cos theta. And in the same way, I can have the unit vector in the theta direction. That is where the thing goes if I change theta. I can write as so if we do it in 2 dimensions, what we're doing is we're taking z and y, for instance, or x. We're taking we're looking at these 2 directions, that direction and that direction. So we're trying to find out the unit vector in that direction and the unit vector in that direction. But we do this now in 3 dimensions. And the way to construct it quite easily is to do the projection first just in 2 dimensions, because then you can't really make a mistake. And then you call this thing, as an intermediate, you call it rho. You project it in that direction. And then you do it a second time. And then you use these two ways of projecting that. I think you can find this in many textbooks, and I think it's not physics, it's applied mathematics. So all of you will probably know this very well. But so maybe I shouldn't even go and write all this down. Is it okay? You know all this? You don't know that? Yeah. I think it's easier if we look at I can give you a page. Well, I can write it down if you want to. It's quick. So now this thing becomes a cos here, cos theta, and cos phi, and plus y, and this is again a cos here, theta and sine phi, and then this is a minus z sine theta, and the last one is minus x sine phi. I'm sorry, I'm using different ways of writing phi. So let's stick to this one. This is minus. This is sine phi plus y cos phi. Now, the one thing, if you've done this calculation, as I said, you can check it yourself very easily by doing it in 2 steps. Is it? Minus sine phi, cos phi. Sorry. This is phi, yeah? This is the vector phi. Okay. So this is the way it looks. Now the thing to do, just in order to make sure that you have reached the correct answer, is to just check that you indeed have a coordinate system which is orthogonal. So you should take the dot product of this and that must be 0, and you can check that. and you take the dot product of this and that must be 0 too, and you take the dot product of this and that must be 0. And if that is a fact, then you have an orthogonal coordinate system, and you can work with it. And so the way of this program, which I'm outlining here, is actually quite messy. It now says I have to find R dot. And R dot is the R dt, so that is equal to d dt of R times R. And remember, they now both change because things move. The unit vector will change, and the length length along that unit vector will also change. And so you actually get already two terms here. You get dr dt unit vector, and you get R times dr dt. And now if you calculate, now you go back to that and you calculate dr dt, you get for this thing, you get theta dot, I think. Anyway, if you calculate this thing, let me see, dr dt. Oh yeah, so I have to calculate this thing, dr dt, and for that I have to go into that equation, and if you go and do it, you get dr d theta dt, and plus dr d phi dt, okay, and now you have to go and find what is dr d theta. You differentiate it up there, and you have to find what is the RT phi. You find it up there again, and then you collect all the terms. And I've even done that, so you can check yourself that you can do that. You get, for this thing, you get theta. I think this is right. I'm not sure even. But you can do, you can, I mean, that's the sort of thing you get. Phi dot. And now you're not finished yet. Now you have to calculate the second derivative. So you have to do this once again, a second derivative and so on. And so it becomes quite a messy thing, lots of equations and so on. And there must be a simpler way. And So that's why I'm not taking this too serious. I'm just showing you how the way goes rather than working it out in detail. And the thing to realize, and this you do in many problems in physics, when you get a three-dimensional or many-dimensional problem, you try to reduce it to a problem with less dimensions. But how can you do that? I mean, we tried up there with X and Y and Z, but we couldn't because they were tied up. So how do we do it? Any proposals? How I can do this in a smarter way than this? I must look for conserved quantities. I must look for things that are, you see, I'm moving in a multidimensional space in general, but if I move on a surface, on some surface in that space, then that surface is a dimension less. And if I move on another surface in that, then it's another dimension less. So I have to try to reduce the dimensions by saying this thing has to move on a specific surface. It cannot move anywhere in this area. It has to move in very specific places. And so the way, so we are using, and if something is restricted to a certain surface, that means we have a conserved quantity. We have a conserved quantity, and that conserved quantity makes sure that the thing stays on a specific surface. And so this thing is moving around, say, and if it moves around, it has angular momentum, and it keeps on moving around, for instance, this Earth around the Sun. So I think, what about angular momentum? Couldn't that possibly be a conserved quantity in my problem? And so I will define angular momentum. Who knows what it is? Okay, so R cross P is the angular momentum. It's the momentum, and then with the distance multiplied, and it's the cross product. So if the movement is in a circle, and P would be going in this way, R would be in this way, and the angular momentum would show out of the board. So it would be perpendicular to it. And if I look at that quantity, I just want to check whether that could be conserved. Is it? So what we have to do is we have to calculate and now we look at the equations of motion. What is the r dt? V. And what is V? P over m. So it's P cross P. What is P cross P? 0. Okay, so we're getting somewhere. What is the P dt? F. And what can we say about F? In which direction is it?
The same direction
with R. So what is R cross F? 0. So this is 0. So we have here that dP dt, dl dt is 0 for a force which is in the direction R. Not for any force, but for this specific force. It is 0. And so we can use this in order to solve our problem. And the way we can do it is by looking at L squared. We write L squared is L dot L, and and that is equal to R cross P dot R cross P. And now you have to know some vector relations. And this thing is, if you have a thing like that, it is R dot R times P dot P and then you have it's basically this with that, and this with that, and then this with that, and this with that. So it's a minus sign, I think. Minus R dot P squared. And so what is this thing? This is just equal to R squared P squared. And this thing is I write this now as R times R. So then I get R squared, and R dot P with the direction just tells me that's the rth component of P. So I get, so if I take the rth component, I look at P and I divide it up into an R component, a theta component, and a phi component. So it's the R component of P, and I get it there. And now you can see what I'm actually heading for is that H, I want to calculate H, and that is equal to P squared over 2m. This is now P squared as a vector squared, P squared over 2m plus V of R. This is the thing I want to calculate. Now here I have an expression for P squared in terms of L and PR. So what I get here now, that this thing is I divide the R squared through, so I get PR squared over 2m plus and plus L squared over 2m r squared, and then I still have v of r. So this is now my problem, the Hamiltonian problem which I'm looking at, which is different from what I started. In what respect? Why have I achieved, why am I so proud that I've achieved this? What have we achieved? We started with this thing, and now I've written here and I say this is a great success. So why? Why is it simpler? We've made a three-dimensional problem a one-dimensional problem. Huh? And so we have, this is now a one-dimensional problem. We just need to worry about P of R, the momentum in the R direction. And the momentum in the other directions are contained in here. But L is a conserved quantity. So if I know what L is, I just put it in there and it stays the same all the time. And so I have a very, very simple problem now in that I'm looking at a problem with a motion in one direction and in a new potential. And the new potential is this thing, which I will call, everybody calls it that way, I will call V effective. This is an effective potential. It depends on R, and the momentum is, and this is the momentum that is in the R direction. And so I have a totally one-dimensional problem from the three-dimensional problem. And I'm spending some time on this because this is a very general way of solving problems, of finding symmetries, finding that those values of those symmetries. Here the symmetry is the angular momentum. The symmetry is actually the fact that the space is symmetric for rotations. It's a rotational symmetry. The problem doesn't really change if I change the angle. But nevertheless, the thing moves in the angular direction, and the quantity that carries that is a conserved quantity because we have that symmetry. And this is quite a general problem, which we have throughout physics. So I want to draw this now. We had this V going like this. K is negative. Goes like 1 over R like this. And we have another term here in the effective potential, which goes like this. And the problem which I need to solve is the combined problem of these two. And that looks like this. At first this wins, and this is negative. And for very small values of R, this guy wins because it's 1 over R squared. And so it looks like this. Okay? So this now is V effective, the function of R. Looks like this. And what you can now see is something which we call the possibility of a bound state. So we can have a body like the sun, which is moved, like the earth, which has moved into the area of the sun, but it is not free to run away. Anything that sits here can run away, but it is not, because its total energy, this is a potential, and its total energy is say around here. And so the only thing it can do, it can move a little closer and it can move a little further away, a little closer, a little further away, but it can't go away. If you want a rocket which does this, a satellite which does the same, it moves, it can either sit here at this point, where it doesn't move in the R direction at all, it just does the rotation in a circle, or it can be in a little higher energy and then it still does its circle, because that circle determines this thing. It still does that, but within that circle it moves out and in and out and in all the time, you know. So it moves, and that makes that circle an ellipse, and we will discuss that a little further, how that works. And normally people don't tell you the planetary movement in this way. They start off with the ellipse, but this is the way the ellipse, you can say, is being created. It is you just have to look at this one-dimensional problem and say, what is the, well, you have to know what is L, what is the rotation of how quickly does it go around, and that determines the this part of the effective potential, and then you and once you have that, you have this curve, and in this curve you can read off very quickly. If the energy sits here, you are in a circle. If the energy is a little higher, you are not in a circle. You're moving in that circle, but the circle gets bigger and smaller all the way, and that is how the ellipse is being formed. And if you are still higher and higher, and you get to this value, what happens? Yeah? Hyperbolic. Yeah. So what happens then? It moves away. It is not bound to the system. When it comes from somewhere and it approaches us, it doesn't hit us head on. It hits us with a bit of a difference. Fortunately, they don't all hit us head on. It comes a little past like this, and then it goes around, and then it moves away. And what it does is it comes from far away, and it has this energy, and it goes up to here, and this angular movement shields us, that it doesn't hit us, it doesn't come right to the center, it comes up to here, and then it turns back and it goes out. So this is a nice way, for me at least, to look at planetary motion. And I think on Monday I will just do a little more about it, and then you can have had a look and maybe ask some questions. There is a very interesting problem in the movement of planets, is that planets do not, you see what I'll do this again, so don't worry if you don't understand everything. We'll do it again, and you can ask me and all sorts of things. If you have the sun here, and you have a planet that is moving like this on an ellipse. That's the sun, and this is the. So what this planet is actually doing, it's making this movement and this movement, and those superposed onto each other make this ellipse. But it makes any ellipse. It can make many ellipses. The interesting thing of our planets is, well, first of all, the planets stay in a plane. That you can see, because angular momentum is a conserved quantity. If it would turn like this, you would have to add angular momentum, because then the angular momentum would show in a different direction. But if the angular momentum is defined in this way, then it has to move in this way. And to turn it, you have to put in a lot of angular momentum, change the angular momentum direction to get it run something like this. But there's nothing that stops the planet, one would think, of not, once it comes round, not going next time going this way, and the next time going this way, and the next time going this way, and so on. It always ellipses around this point, but different, the ellipses in different directions. They still all show in the same direction. But nevertheless, most of our planets, except a little bit about Mercury, which is an interesting story in itself, they stay in this in this one form. Now the question is why? You see, in physics, if you see something, you always ask why. Huh? And I'll explain it to you on Monday. And what is interesting, I'm just, the property which I will use to explain it to you actually carries on into quantum mechanics. You can see it in a very different way in quantum mechanics also, in a very different way, and I will discuss that as well. So you can already imagine it must have to do something with why. What must the answer be? Energy? What must the answer be? Why would something like this happen? Well, I'll tell you, and we'll do that. There must be another conserved quantity which we are not aware of. There must be something else that is conserved which actually makes sure that happens. No, it's not spin. It's a very special construction. So what you see in this, and this is why I'm spending some time on this specific problem, is that the conserved quantities play a huge role in determining motion, classically already, and then very much more so in quantum mechanics. And so this is something I like to emphasize. We will have to, when we start doing a little bit of quantum mechanics, very simple quantum mechanics, don't get scared, we will also concentrate on these things that are conserved, things that do not change. and you can count on them. They are there. Okay? I think we must break, and I think you must then go to the lab, Emma. Is it good? You want to have another discussion, and then on Monday we have a class again? Have another discussion, and we will come around.